today, arc length and surface area in polar. And here's a prompt. We are going to take this lemniscate and then revolve it about the x-axis. Holy cow, right? And then it's going to create a couple of teardrop dumbbell looking shape. We want the surface area of that thing. Oh boy, okay. Now, so we need ds, right? And then you rotate that around. So let's figure out what ds is. Let's get a little bit of theory out of the way, right? Shall we? Okay. So this is some part of the polar coordinate. This is the pole right here. And this curve is like moving along like that. All right, in that direction, let's say. Then let's try to figure out this length is dr on that side, correct? And this gives you approximately the right triangle. The question is, how long is this thing? Is this the theta? What do you say? It's a trick question. That's not the theta. The theta means right there is the theta. Get it? Out of unit circle, this is 1. So what is that thingy? Arclength formula, I only talked about it yesterday, you know.
R d theta?
R d theta, good, thank you, right? Arc length is R theta, so if that angle is d theta, infinitesimal angle, so this is infinitely skinny sector. You know what I'm saying? Okay, and then there's no guarantee that thing moves with a constant radius, so it's like made it slanted. So Pythagorean theorem will apply, right? So that ds is equal to, in this case, dr squared, r d theta, r squared, d theta squared, plus, and then this one, dr squared. You know what I'm saying? Okay, so didn't I tell you there are 4 different variations of ds? Let's quickly review those. Let's bring those back. So in Cartesian coordinate, remember Pythagorean theorem, dx squared plus dy squared, right? And depending on what you need, you can factor dx out, then this becomes 1 plus dy over dx, quantity squared. Or you can factor dy out, then this becomes dx over dy, quantity squared plus 1. Or lastly, we did this, dt in parametry, just a few sections ago. And then this becomes then dx over dt, also known as velocity x component, plus velocity y component squared. You know what I'm saying? This is what's called the speed in parametric, in vector functions. Now, and then I told you someday there's force way, and this is today, that's someday. So we usually integrate with respect to theta. So we factor the theta out, so this will be r squared, and this one will be dr over the theta squared. How about that? You get it? So that's the little bit of theory behind this thing. All good? Now we're going to go get this thing. Okay. Okay, I'm going to write dA over here. So that much is ds, and I'm going to revolve that about the x-axis. So the shape that it's going to create is like this, isn't it? Change that to my usual green color and move it slightly this way. So this is the onion ring that we create. That's my dA. Okay, so let's get the dimensions. This much is still y, isn't it? Because remember our dA was y times ds, wasn't it? Wasn't it? That's ugly y. Okay, what's y in polar coordinate? This is polar coordinate.
r sine theta or something?
Yes, of course, r sine theta. Yes. Good. Figure out what ds is. Wait a minute, what's r is that thing? You square root of cosine to, oh my god, right? One thing at a time, good thing happens to those who wait. So we'll come back here to this picture. We're going to find the r over the theta first, shall we? Let's do that. So here r squared is equal to cosine to theta. Okay, now we do not want to take a square root of this and then do a chain rule. Oh no, that's unthinkable. So let's review. Do you still remember implicit derivative? We differentiate both sides with respect to theta. So this will become 2r, then chain rule will give us this. Remember this thingy? And this thingy will be negative 2 sine to theta. With me? So the r d theta will be dividing it by 2r, so we have negative sine theta over r. Should we substitute that thingy? R square root cosine to theta? No, leave it. Good things happen to those who wait. Okay, trust me on this one. I've seen this movie before. Okay, let's calculate ds. Well, ds was square root of r squared, right? I'll just write r squared. I know it's tempting to put that. No, r squared is okay. I mean, cosine to theta will work. And then plus dr over d theta, this thingy, right? So let's put sine squared theta over r squared. I'm gonna make the square root a little bigger. Good.
Wait,
Whoa. Yes.
is there supposed to be a 2 before the theta and the dr over d theta?
Where is 2? This 2?
Like in dr over d theta, isn't there 2 after, like in the sine 2 theta?
Sine to theta?
Actually, I think what you mean is
Oh, that's 2. Oh, yeah, 2 theta. I dropped that 2, right? Yeah. Nice catch. Save the day. You saved the day. So this should be 2 theta. Like that, right? That was very good observation. I only did it to see if you're paying any attention. Good. Oldest excuse of teachers, of course. You heard that before, right? Okay, do you want to substitute that r in now? Nope, wait. Common denominator. Common denominator, of course, is r squared, right? So we have r to the 4th plus sine squared to theta a. Say yes. Say yes. Now you substitute. Okay, r squared is this, so we will have cosine squared there, right? So we'll have cosine squared to theta plus sine squared to theta. Aha! And we'll put the square root that much and over r, square root of r squared. You get it? Do you see that's 1? I told you good things happen to those who wait. So this is 1 over r theta. Why is it still not substituting that r now? Don't we have to substitute at some point in order to integrate? I say still wait. Okay? Now we know what ds is. So remember this thingy? We'll go back and plug it in here. Do you see why I did not want to substitute? I'm gonna plug it. ds is right here, and that ds is 1 over r. 1 over r. R's cancel. Ain't that nice? You know what I'm saying? Oh, I screwed up. Can you see where I screwed up? This is not just pi ds. I need a circumference times ds. I did the radius times ds. Somebody give me a formula for the circumference of a circle?
2 pi r.
2 pi, right? So 2 pi is missing 2 pi r ds. You get it? So I will put 2 pi back in. Now this is a very, very nice integrand now, isn't it? Okay, let's integrate. So our a here is, now here's the thing. Do we do 0 to 2 pi? Somebody's shaking his head. Tell me why not, Josh?
Is it because of symmetry, or I know it's probably either because of symmetry or since 2 pi, the thing will go around twice.
Ah, in polar coordinate, you almost never want to do such a thing. Okay, let's talk about, in this case, it actually creates even bigger problem, but in nice cases, I mean, if it's nice, then wouldn't it work anyway? We'll see. Let's review the polar graphing here. Say we want to have nice y is equal to sine thingy. I mean, r is equal to sine theta. This thingy. Let's just talk about this thingy. Okay, this is nice. R is equal to sine theta, and so this is 2. You know what I'm saying? Feel it? How many loops are here? There are 2 loops, right? First it goes around, and if that's why I gave you the polar graphing quiz. You know what I'm saying? There are exactly 2 loops. So what happens if you do 0 to 2 pi? You get double of exactly what you want, because it goes around literally twice. You know what I'm saying? So you have to literally, you have to know what you're doing. Otherwise, you might get double, triple of what you want sometimes. You get it? So you don't want to do such a thing. Always use symmetry. So if I'm integrating either finding this area or that arc length, I will only go from 0 to pi over 2 and double it. I will take the minimum amount I can see, then I use symmetry. But in this case, problem is even bigger than that. So let's see, if you go from 0 to 2 pi, do you know that this thing disappears? And this gives you imaginary number. That's why this thing doesn't exist. The four petals, a couple of them disappear, because when you have 2 theta, that creates 4 petals, but there are only 2. And reason for that is because it disappears. This is imaginary part. This cosine of the square root becomes negative. So what angle does this thing disappear? What's that angle? It appears to be pi over 4. How do you calculate it? And then it doesn't appear until this point, which is of course 3 pi over 4. But how do you calculate it? How do you know when this thing disappears? You set this r equal to 0. So cosine 2 theta is equal to 0, then you get pi over 4. That's when it disappears. And you really don't want to sit and investigate when this thing re-emerges. You know what I'm saying? So the best thing to do is never do such a thing. And then you just put pi over 4 here, and let's think about symmetry. So we got that much, and we are going to revolve it. So that gives you this entire half surface area. So we only need to double it. You get it? Did you all get it? So never put 0 to 2 pi unless you really, really know what you're doing. There are so many things that can go with it. If you evaluate this thing from 0 to 2 pi, I mean, it'll evaluate it for you because we simplified it enough. This calculator is not going to know the difference. You should know better. And then we put this nice thingy, integrand. Now it's downhill. The integrity is like not that much required. Okay, so we have 4 pi, and this thing, of course, becomes negative cosine theta. And use plumbing professor as always, right? So this minus that, so we have 1 minus root 2 over 2. Good. And if you want to make it look pretty, I mean, I would take that, distribute only 2. So we have 2 minus root 2. How about that? We want this area right there, right? Okay, there's no way you can do this with one integral. Do you realize that? Because I'm gonna draw this partition, and the partition will go right here. Okay, now let's just look at this one side at a time. This area right here, that curve, is this R, which belongs to this function A. And then the other one, this one, belongs to that function. So either we do two separate integral, or we use symmetry. Okay? So this is definitely pi over 4, isn't it? Do you see that? Okay, I mean, we can set them equal to each other and solve it, but I think you guys know this much, right? Okay, then which half is easier? Well, if you want to go from 0 to pi over 4, we are using this circle, right? That one right there. Or you can go from pi over 4 to pi over 2. But then 0 is our favorite number. You know what I'm saying? So let's just use this one right here. We get it? So let's see how well this thing works. If I try to throw a triangle right there, did it work? Ah, it didn't. Almost worked. But I think I can make this thing work. Hold on. Let me, oh yeah. Okay, how about that? So that's my dA. Okay, let me change the color of this thing. So this is my dA right there. Okay. So dA here is 1/2 r squared d theta, and that comes from area of a sector formula. Okay, and we are using this function, right? Okay, so let's plug it in. So that will be that square, so we'll have 2, right? And then sine squared theta to theta A. So far with me? And then, do you know what to do with this? What is sine squared theta? Oh, here we go again. This thing never goes away. Somebody tell me.
1 minus cosine 2 theta and, or sorry, yeah, 1 minus cosine 2 theta,
Yeah.
and then over 2 cancels.
Over 2 cancels this too, so we'll have 1 minus cosine 2 theta. The theta is all we have, right? So far, so good. Now then, we can integrate, right? So we'll say A is symmetry and 0 to pi over 4, eh? So far, so good. Okay, because we are only taking this half of them and we want this entire area. Okay, and then we put that in. So 1 minus cosine 2 theta, d theta, 8. So that is 2, and this thing becomes theta, and this thing becomes sine 2 theta, therefore 1/2 here. Good. 0 to pi over 4. You with me? Okay, so that is 2, and then this is pi over 4, and this is pi over 2, right? Is that minus 1/2? Well, 1 with half. Let's distribute 2 to make it look pretty, right? So we have pi over 2 minus 1. How about that? Good. Say yes. Okay, then we'll move on to number 29. Okay, number 29 is graph of a tangent, and of course, the picture is not syncing. That's weird. Is it? Oh, it's synced. Wow, okay. Tangent looks like this, right? Okay, and then there are asymptotes, but hey, now area of between negative pi over 2 and pi over 2. Okay, and pi over 2. Wow. So what? That's asymptote. Is that infinite area? What are they saying? It's a shaded region, so this is it. So it's just that. Okay. Oh, there are two separate problems. I didn't read it correctly. So that's A, and then B is just potentially infinite area, right? Okay. As if the graph of tangent could be as. So is this, if we draw this line, is that the asymptote, right? Okay. Alrighty, I didn't copy the picture for the second one, so why don't I do that? I'm making a copy of the picture. And it'll appear right underneath. Okay, this is the picture that they're talking about. It's too big, so let me resize that. Okay, so this is for part B. Two separate problems. So you guys want A and B both, right? I'm presuming. Okay, let's do it. So if in this picture, do we see that this is pi over 4 right here, the angle? Or do we need to calculate it? Do you want me to calculate why this angle is pi over 4? Ne, you got it? Okay, so this angle right there is pi over 4. Okay, then, of course, this side and right there, our function changes on us, right? So there's no way to do this. See, whenever this polar coordinate function is from the pole, origin, pole, to wherever the curve is, right? So this is the tangent theta, and this is just that line. You know what I'm saying? So instead of doing it with a two separate integral, this one we can do it with geometry. Do you see that? This is 1. So this is 1 over root 2, 1 over root 2a. Say yes. So this entire area is 1/4. Good. You want me to teach you how to get that as well, or are we good with geometry? So we'll just calculate this area. That's my A. Okay? So dA now. dA is 1/2 r squared d theta, and our r squared, r is tangent theta. Good, this thing right there. Okay, so let's do this. So 1/2 tangent squared theta d theta. You with me? Okay, how do we integrate tangent square? Somebody tell me while I write
Separate
this.
it into secant squared minus 1.
Yeah, of course, right? Secant squared theta minus 1 is how you integrate tangent squared. Okay, and then you see how nice it is to use symmetry in polar coordinate because the formula itself has 1/2. And if you double it, they cancel. Okay, so now I have those two cancel, so secant squared becomes tangent theta minus theta. And this is where we were, right? So far, so good. Okay, then pi over 4, tangent pi over 4 is 1a. Say yes. Okay, minus, and then this thingy, pi over 4. So far, so good. Okay. Now, if I double it, I calculated all of this, and then that side as well. You know what I'm saying? So I got that. So our total area, we have to calculate the area of a triangle now, don't we? So let me bring this down a little bit. So the total area, this computer's acting up. Total area is 1 plus 1 minus 5/4. And then plus area of that triangle, which is 1/2, eh? Say yes. So we have 3/2 minus 5/4. Are we good? Okay, then let's go down to this problem. So this problem says, well, if we draw the x is equal to 1 here, then, well, that looks asymptotic. So is it an asymptote? How do we show that? Right, okay. Do you see that this is x is equal to 1? Do we even know that? Do you want me to show you how to convert x is equal to 1 to polar coordinate, or do we know this? You don't know this. Okay, let's do that much. See, x is equal to 1, right? X, of course, is r cosine theta. And then divide by cosine theta, so r is equal to secant theta. It's that one right there. You get it? Okay, now, and then if I draw this line and the gap distance between R1 and R2, R1 is our tangent and R2 is this line, there's that tiny little gap, right? R1 and R2. If we take a limit and change that, move that line all the way up towards pi/2, would this gap become 0 is the question. That's what asymptotic behavior is, right? The distance between the two gets smaller and smaller and smaller, and eventually it approaches 0. You get it? So what I want to find out here is the limit of R1 minus R2. Technically it's absolute value, but I think with this, if it's becoming 0, it doesn't care. You know what I'm saying? And then we'll approach theta as pi/2 from the left-hand side. How about that? Good? Do you understand this type of thinking? AP has done this kind of problem, one minus the other. What does it look like? It looks like that much right there. You get it? Okay, then let's see what this thing becomes. So we have limit of theta approaching pi/2 from the left-hand side. Did I say from the left-hand side and put plus sign? Okay, and then R1 is tangent theta, right? And then R2 is secant theta. So far so good? In the Dropbox note, I might have done R2 minus R1, but this is slightly negative because R2 is bigger. That's why I did it that way, but doesn't matter. 0 doesn't care. Okay, so this is vertical asymptote is at pi/2, and vertical asymptote secant is at pi/2, right? So this is infinity minus infinity. How did we deal with infinity minus infinity in chapter 8?
Take the derivative.
Common denominator, right? So this is sine over cosine, and this is 1 over cosine, like that, eh? Now, let's check. So pi/2, this is 1 minus 1, 0, and cosine pi/2 is 0, so we have 0 over 0, so we can L'Hopitalise now, right? So this is same as theta approaching pi/2, and derivative becomes cosine theta, and over this thing becomes negative sine theta. So far so good? Now, and this thingy, cosine pi/2 is 0, sine pi/2 is 1, so this is 0, eh? What did we find? limit of the difference of the two, I mean, technically it's absolute value, but 0 doesn't care, approaches 0. That tells you this is the asymptote, right? So then we can say r is equal to secant theta, which is really x is equal to 1, right? This function is asymptote. Asymptote is a really weird spelling, isn't it? R is equal to tangent theta. How about that? Good. Okay, so that's all from Thursday night. So let's go to Friday night's homework. Okay, let's see what we have. What's the first one? 35, right? Okay, let's go to 35. So we have, do we know that this is a parabola? Do you remember doing that part, converting this to Cartesian coordinate? I mean, we don't care, we don't have to know what it looks like, but this is a parabola. You want me to show you? How many of you want to see it? This being parabola. Okay, let's see it. So we multiply this denominator over, so we have r plus r cosine theta is equal to 6. Good? Say yes. And then r cosine theta is x, isn't it? This thing is x right there. Okay, so before we can square both sides, that becomes ugly, so we'll isolate r and then bring it over, so we have 6 minus x. Now we square both sides. R squared, of course, is x squared plus y squared, eh? And this thing squared, so 36 minus 12x plus x squared, eh? And x squared cancels, so we have y squared is equal to, let me write it this way, negative 12x plus 36. Do you see this is a parabola now? Ooh. Wow, this computer is really acting up. You know what I'm saying? Okay, now, but we really don't need that, okay? We just need to find the length of the line, right? So, what was the ds formula? ds was square root of, what was it? Or should we go back and figure it out again?
Isn't it r squared plus dr squared?
R squared theta plus dr squared according to Pythagorean theorem, right? And we factored ds d theta out. So it looks like this. You get it? Now, so we need the derivative. So let's take the derivative. Right? Thinking of this as a -1 power, right? So we'll take dr d theta up here, dr d theta. -1 power, so we'll have -6 and then -2 power. Like that. And then chain rule, derivative of this. So make this back to positive and then sine theta. You get it? Say yes. Okay, so this ds now is equal to, shove that in. Oh, okay. Let's think rationally. R squared, so we have that thing is squared, so we have 36 inside, And then we are going to square that thing. We also have 6. So 6 at least is a common factor, eh? Then we'll have, oh my God, 1 over, this is a calculator problem, isn't it? Better be. Plus, and that thingy square, so we have sine squared theta over 1 plus cosine theta quantity squared, eh? And then d theta. How's that? Good? Okay, now, can we do something about it? Yeah, we can convert this into, let me think about this a little bit, push this thing down. Okay, now at least the denominator is nice, right? Okay. So what we have here is 6 square root of 1 plus sine squared theta, and the denominator is just 1 plus cosine theta, eh? So far with me? Say yes. Sarah, do you have a question?
Yeah, so when we're squaring the derivative, shouldn't the denominator be onto the 4th power?
Oh my God, no, you're right. I forgot that. So this is squared, eh? Nice catch. That's a nice catch before it was too late. So this is 4th power and this is 4th power. Okay, that was great. Then what do? Could we do something about this? 1 plus sine squared. What is sine squared? Or should we just shove the whole thing into a calculator since it's a calculator problem anyway? I mean, in the Dropbox note, I tried to simplify it a little bit, but then now I'm thinking, why did I do that, right? So after this, let's say it's calculator. How about that? Because I don't see how we can integrate this thing, even if we simplify it. Okay, so after this is calculator. How about that? Good. Okay, so moving on. 36. Is 36 about the same thing then? Yeah, 36 is about exactly the same thing, isn't it? Okay, so let's not do it. It works out about the same way. Wait, actually, I think there is a way to integrate. No, we can't. Still can't integrate. It's one of the ugly ones, so let's not. Okay, let's do 37. 37 requires a picture, so I'm gonna put the picture. Let's see if it's the one. That's the one piece. So let me make a copy of that picture. Okay, here comes the picture. Okay, so we have this curve. I'm gonna push this thing down a little bit. A little more would be nice. Okay. Let's see what they want. So we have a curve, cosine square. I don't understand the picture. Is this thingy is both of them? What's going on?
That doesn't look like 0 pi over 4.
Yeah, what is this? I just got it from the Dropbox note, but this does not look right now, does it? Yeah, let's forget this. I'm gonna just get rid of it. Because in this case, we really don't need to know what it looks like, right? We just need a derivative. And this is another calculator thing. Let's just do that much. How much time do we have left? Yeah, I think we can pull it off. So we need DRD data. So that's the first thing we do. So this is 2 and cosine, and then theta over 3. Good. And then chain rule, right? Negative. So we change this to negative now. Negative. And then sine theta over 3. And then the chicken turducken, another chain rule, plus over 3 here. Good. Say yes. And this is a hot mess if you want to plug it in. So what I did was change that to negative 1/3, and then sine, and using double angle formula.
Mr. Kim, should I just send you a private message with the FRQ? Or where should I
not make the assignment to turn in?
Oh, should I just do the old one from last week?
No, that has been locked. Oh, okay, just yeah, send it to the chat message to me.
All right.
Yeah, let's make it as an attachment, and then yeah, I forgot to do that. So okay, alrighty. So first circuit, then DS. It's doing all kinds of things. DS is equal to square root of R squared. So we have cosine to the 4th power theta over 3 plus this thing is square, right? So 1/9 of sine squared 2 theta over 3 and the theta. Okay, and then in the Dropbox note, I made some attempt to simplify, because at the time, not knowing whether this thing can be integrated or not by hand, and turns out it's not possible. Which, if that's the case, then we can just plug this into the calculator. You know what I'm saying? And then let's not bother, because many of you did this on the last test. If you see a calculator icon, don't be hand evaluating, because it doesn't do anything. There's no additional point, okay? So just put it into the calculator. Don't just waste your time. You get no points for that effort, okay? Okay, and then we'll do this 37 now. Okay, so we have, let me locate that. It also comes with a picture, so let me copy that picture.
Mr. Kim, did you get the chat?
What was that?
Did you get the quiz on the chat?
I'm kind of busy, so I think I did. Let's just trust I did. Okay, so this is the picture. So inside this, but outside of the circle. So it looks like we are looking at this area right there. You know what I'm saying? So far, so good. Okay, then. So let's just think. If we are drawing this triangle, let me zoom in and actually try to draw one for you. can draw it looking like this. That's a tiny little sector that we can, right? That's my dA. However, only thing we want is that much, isn't it? So we are looking at R1 squared minus R2 squared dA. And then we don't have to worry about this portion because we only wanted this part. And I guess this part as well, eh? You with me? So only thing we need is, number one, we need that angle, right? Pi over 4. That is not as obvious, so we'll calculate it, okay? So calling this thing R1 and this thing R2. So we have to set R1 to R2 first. Good? So we have 1 plus cosine 2 theta, and the other side is 1/8. So cosine 2 theta is equal to 0, which means 2 theta on that side, first quadrant is pi over 2. So theta is equal to pi over 4 is how I got this pi over 4. You with me? Say yes. Okay then. Let's calculate dA. I'm gonna do it here. dA is 1/2 R1 squared minus R2 squared. Remember this? Because we take the big sector and subtract the small sector out. You get it? So it's the difference of the squares. So what we have is 1/2, and then R1 squared is this. So we have, let me change that to bracket. 1 plus cosine 2 theta quantity squared, and then minus R2 squared is 1. With me? Okay, and let's square that out. So what we have is 1 minus and plus 2 cosine 2 theta plus cosine squared 2 theta minus 1. Good? Okay, so here we go again, cosine squared, right? What do we do with cosine squared? So one's cancel, so we have 2 cosine 2 theta. And cosine squared is? Oh, come on, children, this is when you shout out the identity. Because how many times have we done this? I mean, this, by now, it should be autopilot.
1 plus cosine 2 theta over 2.
1 plus cosine, this time now 4 theta.
4 theta.
Like that, right? Because it was already 2 theta, eh? Say yes. Okay, let's integrate. So my A is, now we should take just from 0 to pi over 4, because 0 is our favorite number, and then we'll quadruple it. Because we have this one, where's my mouse? We have this one, and that one, and this one. You get it? Okay, and shove this thingy in. So let's put 1/2, and let's do this methodically. This is 1/2 right there, so I'm going to put 1/2 first. And then we have plus 2 cosine 2 theta. And then this is 1/2 cosine 4 theta, right? So we have plus 1/2 cosine 4 theta. You with me? Who's lost? Okay then. So these two cancel and gives you 2, and so we have 1/2 theta plus, does this become sine 2 theta and chain rule that cancels that 2, eh? Say yes. Okay. And then we have this thingy becomes sine 4 theta, chain rule, so we have 1/8. Like that, eh? You with me? Okay then. Let's see what this is. So, like I said, this minus this, right? In one shot, so that's pi over 8. Good. We always do this thingy minus this thingy right there. Okay, instead of writing all of this minus all of these. You know what I'm saying? Okay, and then pi over 4 here gives you 0, eh? Okay, so that's gone, and then 0 gives you 0. What about here? This is pi. Wait. Pi over 4 does not give you 0 here, right? This becomes pi over 2. So that's 1. So far so good? So we have plus 1. And then minus 0 gives you 0. And this one gives you 0, right? Because this becomes sine pi, which is 0. So this is it. Should we distribute to make it look prettier, or is it already pretty? Whatever, right? Calculating ds. Okay, we need ds. But before we even do ds, let's just throw ds right there. Before we even do that, what we need is dr d theta, right? So dr d theta is equal to negative 2a sine theta, isn't it? Say yes. Okay, then ds. What does ds look like? Would that be square root of r squared plus dr d theta square, d theta here? Okay, so let's plug this thingy in. So we have square root of 4a squared and cosine squared theta plus, and then this thingy, oh, it's going to turn out to be very nice, right? 4a squared sine squared theta d theta. You see that? Say yes. Okay then.
Yes.
That's 2a, eh? That's one of the nicer looking arc lengths there is, right? Then we're going to have to rotate this about the y-axis. So let me draw that picture in. So it's going to create this looking thingy, right? Ah, that's ugly. What's wrong with my hand? My hands are shaky today. So that's the thing that we want. That's my dA. Okay, so dA now, I'm going to do it down here. dA is equal to 2 pi, and this is x, eh? From here to here. 2 pi x, and then ds, correct? And x, of course, is r cosine theta, eh? Say yes. And then ds is this thingy, d2a d theta. So far with me? And then,
Yes.
of course, r is 2a cosine theta. So putting it in together, so we have 2 pi, 2 here, and 2 there. So we have 8 pi and a square. So far with me? And cosine theta. So we would have cosine squared theta, d theta. Still with me? Pushing these things down a little bit. Whoa, that didn't work. This computer has been acting up since second period. Okay, now, then what do we do with this cosine squared theta? I mean, we have done this many times, so somebody tell me what to do with it.
1 plus cosine 2 theta over 2.
Uh-huh. I mean, this thing should be on autopilot by now, right? Y'all with me with this? Okay, I think this is something we can integrate now, right? So integrating, so your A is, oh, okay, let's think about symmetry, eh? Symmetry from here to here, right? And then we double it to create both sides, the top part and down part. So 0 to where does this thing go into the pole? Do you remember after that graphing quiz in chapter 3? At what angle does this cosine theta go into the pole?
Pi over 2.
Pi over 2, and then we double it, and then we put that entire thingy, the 2's can't cancel 8, so we'll have 4. And then we have pi a squared constant, then we'll have 1 plus cosine 2 theta, d theta, like that, eh? So we'll have 8 pi a squared, and then we have theta, and plus sine 2 theta, and then chain rule, so therefore half, and 0 to pi over 2a. Then plug in pi over 2, so we have pi over 2, and this thing usually dies, right? So that's it, 0 gives you 0. So lo and behold, this is one of the nicer ones, so we have 4 pi squared a squared. How about that? That was great, wasn't it? Okay, now, and then number 33, cardioid, what do they want? Is it a surface area? Or is it just, it's a arc length, isn't it? Arc length of this whole thing, right? Okay, so once again, we need dr d theta. So let's do that first, dr d theta. You see how I do this mathematically instead of starting with a grand formula? That's bad, those are really bad. So which is negative sine theta. Okay, then ds is square, I'll just write it one more time, r squared plus dr d theta, quantity squared. Oh, I made that square root too long. And then d theta, good. So I have r squared, which is 1 plus cosine x theta squared plus this thingy, sine squared theta. I did not make it long enough this time. Good. Now let's expand this out. So we have 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta a. So what we have at the moment is this, 2 plus 2 cosine theta d theta. Now the question is, how are we going to integrate this? Here's a hint. I'm going to common factor square root 2. Actually, I'm not going to even do that. I'm going to leave a space here. I want this thing to look like this, because in maths, many times we can write whatever the hell we want to and tweak it. Why would I want this in this form? Somebody tell me while I push these things down.
It's the half angle formula.
Oh yeah, half angle formula for what?
Cosine.
This is cosine, right? Cosine theta over 2. So how do I adjust this thing to make it look exactly like that? Is the question now, isn't it? Something times this, right? So if I put 2, for example, would that work? 2 going in becomes 4, cancel and distribute, bang. You know what I'm saying? Do you see how that works? Okay, so this is now nice. This is 2, and then cosine theta over 2. d theta. Oh, that's very nice, isn't it? So only thing we have left is to integrate. So let's integrate. So our s, I'm going to do it here, is from 0 to, at what angle does this thing go all the way around and then enter pole now? You have to know your trig graphs. I mean, oftentimes what it looks like is what it is, but then it's not like I'm going to give you this graph on the test.
Pi.
Pi. And then we should double it, right? Good. Okay, then we lay this thing down. Like that, eh? Okay, after that it's all downhill. So it's 4. So far so good. And then integrate. So is this sine theta over 2 chain rule? We need 2, eh? To cancel that thingy coming out. And it's positive 0 to pi, eh? Say yes. Okay, so this thingy is 8. And once you plug in pi, it becomes pi over 2. That gives you 1. Plug in 0, that's 0. So this is it. How about that? Good. Any other question? Okay, moving on. 35. 35 is not that we need to know, but do you guys know this is a parabola? Have you ever converted this to a parabola before? Let's do that for you. Okay, this is a nice exercise. So let's just convert this to a parabola and see. I'm going to multiply 1 plus cosine 6 to both sides. So I have r plus r cosine 6, right? And cosine 6, cosine theta is equal to 6 is what I meant to say. So far so good? Then, do you see that this thing is x? Yes, it is, huh? So that's x, and then I'm going to bring it back to the other side before I square both sides. You with me? Now we square both sides, so r squared is x squared plus y squared. And this is x minus 12x plus x squared. Eh? X squared cancels, so we have y squared is equal to 6 minus 12x. Huh, do you see parabola now? I mean, I don't have to solve it for y, right? So it's like parabola going this way, you get it? Actually, it's kind of a bad parabola. You with me? Okay, so not that we needed that. So we need dr d theta. Okay, think of this as a negative 1 power. So dr d theta is equal to negative 6. And then negative 2 power. Can you think like this? Negative 2 power. And chain rule. So negative sign, so make that back to positive. You get it? Good. Now, ds is kind of ugly. I mean, it's very ugly. Square root of r squared. Let's think like this. Here's a 6. Here's a 6. We're going to square them. So we'll have a common factor of 36, which we can take it outside here and then put 6. You know what I'm saying? You see that? Okay, then we'll have 1 over 1 plus cosine theta squared plus this one. So we'll have sine squared theta over 1 plus cosine theta to the 4th power. How about that? So far with me? we could try to simplify this, and I did on the Dropbox note, but turns out this is a calculator problem anyway now, doesn't it? Right? Which means it's so much wiser to just shove it in the calculator now, instead of trying to simplify it. Many of you made that mistake. When you see that calculator icon on the test problem, that means this is now is a time to put it into a calculator, not simplify it, or some of you actually decide to integrate it by hand, then get a numerical answer. You do not get any additional points for that kind of effort. I mean, now, do it now. You get it? So you can plug it into the calculator now. But on the Dropbox note, I made a little bit of a simplification. Do you want to see how that is done? Or if you don't want to see, we can move on. Shifang.
Oh, shouldn't it be y squared equals 36 minus 12x?
Y squared is equal to, oh my God. That's embarrassing. Yes. Nice catch. Okay, now back to this question. How many of you want to see kind of what I did to simplify this or not? Because we really don't need to. Just say no, just calculator, right? So just calculator now. Okay, we still need to kind of set up, but it's like 0 to pi over 2. They even tell you what to what. So it's like just shove the whole thing into calculator, evaluate it from 0 to pi over 2, and then say we're done. Good? Okay.
If you're at that point of the problem, how can you tell it's a calculator problem?
No, this.
Oh, just if it has the icon?
Yeah, that calculator icon tells you if, see, that's one nice thing about the AP, unlike your textbook, AP Classroom, it shows you the icon, right? That means you can use calculator. I mean, if you don't see the icon, you can still use a calculator, but your solutions, whatever you present, has to be as if you didn't have one. Right? Okay, but your textbook kind of mixes these things up, so you have to look at the answer key and then determine whether it's a calculator or not. But AP Classroom is very nice in that part. And then in case we ever come back to school in person, then I have, doesn't look like it, right? Then I will have either calculator test or non-calculator test. There's no combination on my test. Pencil and paper test is, okay? So there's no confusion whatsoever, right? Okay. Moving on then. Okay, let's do 36. Wait, that looks exactly the same now, doesn't it? Almost the same, right? See, let's compare this thing with this thingy. Only difference is this thingy is minus. But other than that, right? Okay. Well then, shall we just not do it? Or still do it anyway? Your choice. We got time. Who wants to see it? Put your hand. Okay, oh, wow, one person wants to see it, so let's do it, okay? So once again, looking at it as a -1 power, so the R, the theta, gonna zoom in a little bit, is equal to 2, right? -2. And then this becomes -2 power, like that. And the chain rule of this thingy, it's just a sine theta now. Correct? Say yes. Okay, and then ds is square root of this thing is squared plus that thing is squared. So we'll have 2 outside, and then we'll have 1 over 1 minus cosine theta squared plus sine squared over 1 minus cosine theta to the 4th power to theta. Good. I kind of see this one actually is slightly different. This one is calculator as well, the way it's meant to be. However, this can be hand integrated with a very long and ugly integral. You want to see it? Oh, actually the other one. This could be hand integrated too. Not that I expect you to be able to do it, but it could. Now I see it in a hindsight. You want to see it? Don't want to see it? Let's not see it. Okay, at this point, then you just shove the whole thing into a calculator. Okay, so let's just put this into a calculator as well. Because AP will never ask you to hand integrate. This takes, I mean, even if I do it right now, it's gonna take me a good 10 minutes to do it.